Hello and welcome to Science in Action from the BBC. I'm JackStewart. This is our weekly dissection of cutting-edge science and what it means to us. And today's programme is one for the archives, because we're marking the discovery of gravitational waves, a moment that future generations will refer back to. We'll also have new work that shows the jet stream across the Atlantic is getting stronger due to climate change, and that is going to make flights slower.
If you add up these figures for all transatlantic traffic, you can calculate that planes will be airborne for an extra 2,000 hours each year. And if you look at the fuel costs, that's going to add over $20 million.
And of course, burning that extra fuel will only make the problem worse, so we'll have a look at that. And bacteria that act like one giant eyeball, how horses read human emotions, and how Neanderthal DNA influences our everyday lives when we talk to our BBC Science team. Every day there's something like between 2,000 and 3,000 planes that fly across the North Atlantic from the Americas to Europe. And we've got new research that says the duration of those flights is going to change, and the reason for that is global warming. Apparently, rising temperatures will accelerate the jet stream, that's the strong wind that travels across the Atlantic, and that will leave westbound flights battling stronger headwinds. Now, Dr. Paul Williams has calculated that this will cause planes en masse to spend an extra 2,000 hours in the air.
Because of those atmospheric winds, and they can be very strong, 200-300 kilometres per hour, planes will try to get into beneficial wind patterns in order to give themselves a boost in speed. And that means departing away from the shortest distance measured along the ground, and they'll actually be covering a route that goes further measured in terms of kilometres, but because they get a boost up from the speed of the jet stream winds, they actually get to their destination quicker, even though they've gone a rather more circuitous route that's involved covering a greater ground distance.
How big an impact do these winds have? I mean, I thought at the type of altitudes planes fly at, they wouldn't be particularly strong.
Well, we're talking here about the jet stream winds. So the jet stream is a high-altitude wind that blows from west to east across the Atlantic Ocean, and at flight levels it can be blowing at speeds of 200 miles an hour, so that's about 300 kilometres an hour. And if you compare that to the airspeed of a typical large commercial plane, and that could be something like 550 miles per hour, which is 900 kilometres an hour, you can see that the jet stream winds are a significant fraction of the airspeed of the plane. So what that means is that if the plane is travelling in the jet stream in the same direction, then it's going to get a quite significant boost in speed. Whereas in contrast, if it's flying in the opposite direction to the jet stream and battling against those jet stream winds, then it really does get significantly slowed down. And this is why, as anyone who's ever flown across the Atlantic, for example, will know, the eastbound flight is usually about 1 hour faster than the westbound flight, and it's all because of those jet stream winds.
Coincidentally, I just got an email from my uncle this morning who had to fly from the UK to Mexico, and he said it was a long flight out, nearly 11 hours due to the headwind, but only 8.5 hours on the way back. So I guess it does have a really significant impact on some of these flights.
Yeah, that's right.
I mean, you had to narrow it down to one particular route for your study, so you looked at flights between London and New York, a very well-travelled route. How much are they affected?
We focused on flights between London and New York, and what we've done is we've calculated the jet stream winds along that flight route are expected to get 15% stronger because of climate change at the point where the amount of carbon dioxide in the atmosphere has doubled. And quite when that will happen obviously depends on our future emissions. We're almost halfway there. We think we'll get there later this century, but will be sooner or later depending on whether we cut our carbon emissions deeply enough. So for example, in autumn we find that an eastbound flight from New York to London is going to get on average about 5 minutes shorter, whereas the corresponding westbound route from London to New York is going to get 7 minutes longer. What that means is that round-trip flights are going to get a couple of minutes longer on average. The consequence is that planes will be spending longer in the air on average.
And presumably burning more fuel as well.
Yes, if you add up these figures for all transatlantic traffic, you can calculate that planes will be airborne for an extra 2,000 hours each year. And if you look at the fuel costs, that's going to add over $20 million to the fuel costs. It's also going to increase the CO2 emissions of aviation by 70 million kilograms, which is the equivalent of over 7,000 British homes. So these changes are just a few minutes on average, which may seem like a small difference, but when you add them up and apply them to all transatlantic traffic, you really do come up with some large large projections for the future CO2 emissions and the fuel consumption and the costs, of course.
And the CO2 emissions, of course, ironically, are what are causing this effect in the first place, because the crux of this is that you're saying climate change is causing the jet stream to get stronger. Why is that? Do we know the science behind that?
It's funny, isn't it? Because when we think about our CO2 emissions, we're normally thinking about the global warming where we live at the bottom of the atmosphere. But scientists are very confident that the CO2 emissions are changing the temperatures in the upper atmosphere too, all the way up to 35,000 feet and beyond. And it's the temperatures there that drive the jet stream and control its strength. And it turns out that the temperature changes that we're seeing at altitudes up to 35,000 feet are changing in such a way as to strengthen the jet stream winds. There's a very tight coupling between the winds and the temperature patterns. If the temperature changes, it sets up a pressure pattern that drives stronger winds. And in essence, that's the effect that we're seeing that's speeding up those jet stream winds.
So it's a complicated picture. And
yes.
Is it likely to apply more globally? You looked at this one specific route, but do you think it would multiply out?
Yes, there's a jet stream all the way around the northern hemisphere, not just in the Atlantic. And, of course, there's another jet stream in the southern hemisphere too. So I'd like to study this next, and I can't give you any robust figures here, but it seems to me certainly plausible that these increases that we're projecting for transatlantic flights will be similarly experienced on other flight routes around the world too. So this could just be the tip of the iceberg.
Dr. Paul Williams there from the University of Reading. And that is it for Science in Action this week, which was produced by Anya Liktorovich. But there's more from us online, bbcworldservice.com.